Jai Hind all. Myself Dr. Amita Asthana, and here we are going to discuss the topic the Zener diode. In the previous lecture I explained the case 1 of the Zener diode, how the Zener diode is working for the fixed input voltage and fixed load resistance circuit. Okay, now here we will see the case 2 and case 3 numericals. So fixed VI and RL variable we have already seen. Just have a look on this. And case 2 fixed VI. Now we will discuss case 2 is fixed VI and RL variable. Right. So here we are going to solve the case 2 and then we will proceed towards case 3 numericals. Right. So as I discussed earlier, you need to find out while doing the Zener diode questions, you need to find out whether your Zener diode is forward bias or reverse bias. It is acting as a ideal component, or it is active, it is on, or it is working as a battery, a fixed VZ battery. So here we need to find out the state, and then the rest part is very easy for you, right? So here we go. Let's say for considering case 2 and case 3, we will really assume that the Zener diode is active, right? After assuming this, we will find out the things, right? So we will assume that Zener diode is no more in the ideal state. It is actually active. It has been actually converted into the battery of VZ, right? It has been actually converted into battery of VZ, and it is now, it is already working in the voltage regulation mode. So this part we have already assumed while we are solving the numerical of case 2 and case 3. If now the question comes, if the Zener diode is working, let's say, if the Zener diode is working, then it must be in the form of a battery, fixed VZ voltage battery. So we will place this Zener diode in the form of battery of VZ, right? Before starting the numerical of Zener diode, you need to replace the Zener diode in the form of battery without any hesitation, and then you can proceed for the Kirchhoff voltage law and Kirchhoff current law, right? It is not similar to the first part where we were we were finding out the voltage across the diode, and then we were finding out whether the state of the Zener diode. Here we have already assumed that Zener diode is on, Zener diode is working, that's it, right? Now here, there is a specific range of resistor values and therefore load current, which will ensure that the Zener is in the on state. Two smaller load resistance RL will result in the voltage VL across the load resistor less than VZ. Zener diode will be in the, off state. Load resistance should not be very, low, and whether. Don't think about that I have already told you that Zener diode is always being in on state, and you can straightforward do the numerical. We need to find out the value of, since here you can see in this particular circuit, VI is the, input voltage. It is in the input voltage. The current is IR. This is IZ and this is IL. So here IZ is equal to IR minus IL, first part. Now I told you that you need to convert this in the form of battery. So whatever I am saying, let us understand by considering one numerical, right? Then you will be able to understand more clearly. Here in this, for the network, determine the range of RL and IR that will result in VRL being maintained at 10 volt. This is the case where, the RL is variable. We need to find out the value of RL minimum and the RL maximum. Okay. Since this particular RL is variable, so we are more focusing on the RL minimum and RL maximum part, right? Okay. The Zener voltage is 10 volts given. The maximum Zener current in the circuit is given as 32 milliampere. Input voltage is fixed, which is 50 volts, and resistance R is fixed. It is of 1000 ohms or 1 kilo ohm. Now, first of all, we will apply the formula VL is equal to into RL upon R plus RL. Okay, and apply this. In place of RL, you will write in the first step RL minimum. This is the trick to solve the numerical, and from this, since VL is equal to VZ, because I told you consider the Zener diode to be the battery of VZ. So VL, make it equal to VZ and solve for RL minimum. So here I have solved this. VL is equal to VZ is equal to VI into RL minimum upon RL minimum plus R. Okay. Solve this, you will get the value of RL minimum, right? So this should be the first step. Now, after finding out the RL minimum, we have to find out RL maximum, because here in the question they are asking determine the range of RL and IL that will result in VRL maintained at 10 volt. Maintained at 10 volt means Zener diode is working in the regulation mode. So here in this particular case, IR is fixed, because if I see this particular loop, VI fix, R fix, VZ fix. So if you apply KVL, then what you will find? Plus VI. From here we will start and we will come here on this particular loop. Minus IR into R minus VZ. All parameters are fixed. This is fixed, this is fixed, this is fixed. So this IR must be having a unique value. Okay. So in this case, IR is fixed. Okay. Now you can again have this RL maximum, RL minimum already we have calculated, RL minimum already it has been calculated, right? If RL minimum is calculated, then RL maximum we need to find out. Now see, now just listen whatever I am saying, it is important. Here this is fixed, this will IR is fixed. Here this current is IZ maximum. Okay, and IR is equal to IZ plus IL. This is maximum and this is fixed. Then this should be minimum. Okay, understand. For maintaining it to a constant value, IR fix is equal to IZ, and IZ is already given, it is maximum. So IL should be very minimum, that is IR is fixed and IZM, then IL should be minimum, because this is maximum, this is fixed value constant, so this should be only minimum. And if it is minimum, then IL is minimum, then RL should be what? It should be maximum, because V is equal to I into R. If IL is minimum, then RL should be maximum, because their product is also constant value. Okay, and this is nothing but VL is equal to VZ. Now the question is being solved. I think there is no problem. So we can frame the questions, and now we can have IR is equal to IZ maximum plus IL minimum. Already we have solved this particular. VL is equal to VZ is equal to IL minimum into RL minimum. Whatever parameters have been asked, you can solve using, put the value and then you can solve. Okay, IL minimum, IL maximum, all you can find out, right? Now case 3, variable Vi and RL fixed. Now this RL is fixed and this Vi is variable. Input voltage is being varied, whereas this RL is being fixed. So we need to find out Vi minimum and Vi maximum. Okay. So we need to find out this thing and this thing. Now in this particular part, IL is fixed. IL is fixed. If IL is fixed and RL is fixed, VZ is also fixed, because VZ is equal to IL into RL. Right? From there, here, this voltage is VZ. VZ is fixed, so VZ is equal to IL into RL. Okay. Then, for finding out V minimum, but we have to target, we need to target for these two values, Vi minimum and VL maximum. So for finding out Vi minimum, what we do is, we again write the same formula. VL is equal to VZ is equal to Vi into RL upon R plus RL. Now we will here note down this particular point. I am writing this as Vi minimum. Okay. Put the value of RL, R and VZ, and you will find out this Vi minimum from the very first formula. Half of the question is done by using a single formula, right? So apply this formula to find out Vi minimum. Next. Now in this particular circuit, this particular question is being given here. They are asking for the Vi minimum and Vi maximum value, where Vz is 20 volts, Iz maximum is 60 milliamperes, and RL is given this particular value, and everything is given. You have to find out these two values that we asked. So we will apply the first formula. VL is equal to Vz is equal to Vi minimum. I told you this, Vi minimum you have to write here. Instead of Vi, you will write Vi minimum. This you have to find out. This RL is 1.2 kilo ohm. This R is 220 ohm. And this is 20 volt. Put the values and find out Vi minimum. Okay. Like this, you can find out the Vi minimum. Like this. By using this particular formula, you can find out Vi minimum. Now, Again, make the circuit. Next step is convert Zener diode into the battery. Make the circuit. And now we are now interested to find out Vi maximum. We are now interested to find out Vi maximum in this particular circuit. For Vi maximum, you have made the diode as a battery of Vz, okay, and now you will apply this. Now understand one more point here. Vi maximum, the maximum voltage is being given by the battery, so it will provide maximum current also. The battery is at its maximum value of voltage, then it must be providing the maximum resistive current to the circuit. Got it? So here IR will be maximum. Now I repeat, battery value is at its maximum, so maximum current will be provided by the battery. So IR is no more IR here, it is now IR maximum. Now we will apply Kirchhoff current law here at this particular node. IR is maximum is equal to IZ plus I. Okay, this is maximum, this is fixed, then this should also be maximum. If IR is minimum, let's say, then IZ plus IL. IL is fixed, then IZ should be minimum. So here this particular concept is very, very important for the third case. You cannot solve without using these considerations. Okay, if IR is maximum, then IZ is maximum, because IL is fixed in this case as I have written here. And if IR is minimum, battery is at its minimum value, then IZ will be minimum because IL is fixed for the third case, right? I think it is clear now. CRL is fixed. Battery is varying. Battery may be at its minimum value. Battery may be at its maximum value. Battery can be at any of its value, but we have to consider only for Vi minimum and Vi maximum, right? Then rest part is easy. Now after applying this particular concept, you can write down this Kirchhoff, Kirchhoff current law and the input voltages, and you can apply KVL. This particular is coming from here. Applying KVL at this particular stage, start from here, plus Vi max minus IR maximum into R plus minus Vz returning to the point, and this equation can be formed. This I already told you, and using these equations you can solve the numerical. Now the applications of the Zener diode, it's acting as a voltage regulator. It works as over voltage protecting device. It may also used in the clipping circuit, and it can also shift the voltages by its across the load resistance I am saying. So you can also shift the voltage level. It can act as voltage regulator. Now the Zener diode has been covered, and thank you.